Hi, good morning to everybody. Today I am going to teach relation and functions. Relation and functions. Last year studied about relation and functions regarding what is meant by Cartesian product of sets. Second, ordered pair. Third one, what is meant by domain set and codomain set and range set. And we also studied what are all the different types of functions, some different types of specific functions and their graphs. And also we studied the algebra of function. Addition of two functions, subtraction of one function from the other function, multiplication of two functions and division of one function by other function. These concepts are basics of relations and functions. In this chapter, we are going to study different types of relations and function, composition of function, invertible function. We will learn some preliminaries what we have learned in the 11th standard. Preliminaries. 1. Ordered pair. A pair of elements listed in a specific order and separated by a comma and enclosed within parentheses is called an ordered pair. Example: A, B. Ordered pair A, B. X, Y. X, Y. 7, 2. These are all examples of ordered pairs. In ordered pair A, B, A is called first element. A is called first element. B is called second element. B is called second element. Now first element is related to second element. Two ordered pairs are said to be equal if their corresponding elements are equal. Two ordered pairs are said to be equal if their corresponding equals are equal. Example: if A, B equal to C, ordered pair A, B equal to ordered pair C, D, if and only if and only if A equal to C and B equal to D. A equal to C and B equal to D. But if ordered pair A, B equal to ordered pair B, A, if and only if A equal to B, A equal to B. Second one is Cartesian product. If capital A and capital B are two non-empty sets, then the set of all ordered pairs such that small a belongs to capital A and small b belongs to capital B is called Cartesian product, and it is denoted by A cross B. Example: A equal to 1, 3, 5. B equal to 2, 4. What is a non-empty set? Non-empty set means a set contains at least one element. If a set contains one element, at least one element, that it is called non-empty set. Set A 1, 3, 5, set B 2, 4, A cross B is equal to, it is a set, you have to open a set bracket, all the elements are in order first. 1, 2, 1, 4, 3, 2, 3, 4, 5, 2, 5, 4. 1, 2, 1, 4, 3, 2, 3, 4, 5, 2, 5, 4 are 6 ordered pairs. Then how to find B class A? B class A is also a set in which the elements are ordered pair. 2, 1, 2, 3, 2, 5, 4, 1, 4, 3 and 4, this is called, this is A cross B, this is B cross A. In general, A cross B is not equal to B cross A. You see the example, what are all the elements in the, what are the elements in A cross B is not equal to B cross A. Therefore, in general, A cross B is not equal to B cross A. But if A cross B is equal to B cross A, equal only if A is equal to B. A is equal to B. Here in this set, N of A means cardinal number of the set. N of A is 3 because it has 3 elements. N of B is 2 because it has 2 elements. Therefore, N of A cross B is 6. 1, 2, 3, 4, 5, 6. Therefore, N of A cross B is equal to N of A into N of B. N of A cross B is equal to N of A into N of B. So, in general, if N of A equal to M, number of elements is N. N of B, number of elements is N. Then N of A cross B is equal to M n elements. M into n elements. Relation is a recognizable link or connection between two persons or two places or two numbers. Example, how two persons are related? A student can relate to a teacher. Student and teacher can be related. If A is the student, B is the teacher, A and B are related. What is the relation? Is the student of. A is the student of B. That A is the student of is the recognizable link. No places. Delhi is capital of India. Delhi is capital of India. If X is Delhi, Y is India, X, Y, X and Y are related. The recognizable link is the capital of. Then 7 and 9 are related. What is the recognizable link? Is less than. 7 is less than. Then 2 and 8 are connected. The recognizable link is cube root of 2 is cube root of 8. So these are all the recognizable link is called relation. To form a relation, we require two persons or two places or two numbers or two quantities. Relation. Now we are going to learn what is relation. Let A and B two non-empty sets. Then a relation from set A to set B is subset of A cross B. That is R. R is relation. R is subset of A cross B. Example, let A equal to 1, 6, 5. B equal to 3, 4. A is a non-empty set 1, 6, 5. B is a non-empty set 3, 4. You will find A cross B. A cross B 1, 3. 1, 4. 6, 3. 6, 4. 6, 4. 5, 3. 5, 4. This is the A cross B. See, we got 1, 2, 3, 4, 5, 6 order. Here, R1 be the relation is less than from A to B. So, we have to write up R1, open a set bracket, write all the order plus which is obeying to this condition. Here, 1, 3 is 3. See, 1 less than 3, 1 less than 4. Then this one comes, see 6 greater than 3, this one comes, this one, then all the 4 will not come. 1, 3 and 1, 4. 1, 3 and 1, 4. Is the relation. This is the relation. R1 be the relation is less than from A to B is only these two order pair. R2 be the relation is greater than from A to B. Now, is greater than, the relation is greater than. Then R2, in R2 relation, what are all the order pair? We have to write the order pair. First element is greater than the second element. Here this note comes this 6, 3. Because 6 greater than 3. 6, 4. Because 6 greater than 4. And 5, 3. 5 greater than 3. And 5, 4. 5 greater than 3. These are all the 4 order pair which belongs to this relation. 6, 3, 6, 4, 5, 3 and 5, 4 are the relation. I can form one more relation. R3 be the relation. R3 equal to a set of ordered pair A, B such that A plus B less than or equal to A plus B less than or equal to 10, where A belongs to capital A and B belongs to capital B. This is order. It is a set builder form. Now, what are all the order pair elements? What are the elements in R3? So the elements in R3 is, what we have to add both the elements, it should be whether equal to 10 or less than 10. 1 plus 3, 4, less than 10. 1 plus 4, 5, less than 10. 6 plus 3, 9, less than 10. 6 plus 4, 10, equal to 10. 5 plus 3, 8, less than 10. 5 plus 4, 9, less than 10. So all the order pair becomes the member of this relation. 1, 3, 1, 4, 6, 3, 6, 4, 5, 3, 5, 4. All are in this relation. Therefore, what is here? Relation is the subset of A cross B or equal to A cross B. Here R1, R2. What are all the elements present in R1? It is also present in A cross B. So it is. We can say R1 is the subset of A cross B. R2. What are all the elements in R2 is also in A cross B. Therefore, we can say R2 is the subset of A cross B. Whereas if you look R3, all the elements of set R3, all the elements of set in R3 is also in A cross B. So we can say here A cross B is equal to R3. Therefore, in concluding that relation is the subset or equal to that A cross B. Therefore, relation is, any relation is from A to B, any relation from A to B is a subset of A cross B. we know how to find a relation from set A to set B. A relation R from set A to set B is a subset of A cross B. It's a subset of A cross B. Now we can take relation on a set, relation on a single set. A relation on a non-empty set A is A to itself. A to itself is a subset of A cross A. A cross A is known as relation on set A. Is known as relation on set A. So we can take relation on set A to itself. Let's take example. Let A equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we can take a relation. R1 being the relation is trace of A. That is, first element is 3 times the second element. First element is 3 times the second element. What are the order pair in R1? First element is 3 times the second element. 3, 1. Because 3 is 3 times 1. Then 6, 2. 6, 2. 6 is 3 times 2. Then 9, 3. 9 is thrice the 9. Then no other relation is there. Only these 3 order pairs satisfy that relation. That thing is thrice of. Next relation is, let R2 be the relation of, R2 be the relation is half of on A. That means first element is half of the second element. First element is half of the second element. What are the elements in set R2? Is here 2 is 1 is half of 2. First element is half of the second element. 1, 2. First element is half of second. 1 is half of 2. Then you get 2, 4. 2 is half of 4. Then 3, 6. 3 is half of 6. Then 4, 8. 4 is half of 6. And 5, 10. 5 is half of 10. 5 is half of 10. So R2 is, we got 5 order pairs. We got 5 order pairs. That is a, we can take a relation on set A to itself. Representation of relation. A relation can be represented 1 in roster form, 2 in set builder form, 3 by arrow diagram. Consider the set A 2, 4, 6, 8, 10, set B 1, 2, 3, 4, 5. We are taking a relation from A to B. The order pairs are 2, 1, 4, 2, 6, 3, 8, 4, 10, 5 is a representing a set in ordered form. We can represent a set in ordered form or roster form. If the set is represented in ordered pairs, that representation is called roster form. Second one, the same set is represented in set builder form or A, B, such that A is equal to twice of B. A equal to twice of B. A belongs to capital A, B belongs to capital B. Here 2 is twice of 1, 4 is twice of 2, 6 is twice of 3, 8 is twice of 4, 10 is twice of 5. Therefore, it is a common property. First element is twice the second element. Then we can represent a relation in set builder form. Third one by arrow diagram. All the elements in set A is 2, 4, 6, 8, 10. Set B is 1, 2, 3, 4, 5. 1 is mapped into 1, 4 mapped into 2, 6 mapped into 3, 8 mapped into 4, and 10 mapped into 5. This type of representation is called arrow diagram. Domain, range, codomain of a relation. Now we are going to learn what is meant by domain, range, codomain of a relation. If R is a relation from A to B, then the set of all first elements, of the ordered pair in our relation is called domain set. In the ordered pair, if we write all the first element as a set, that set is called domain set. The set of all second elements of the ordered pairs in the relation is called range. If we write all the second elements as a set, that set is called range. Symbolically it can be written as domain of R such that or set of A, order pair A comma B belongs to R, and range of R is such that set of B, A comma B belongs to R. That is symbolically. We will do by an example. Let A equal to 1, 2, 3, 4, 5. Let A is 1, 2, 3, 4, 5. B is 4, 5, 6, 7, 8. Let A 1, 2, 3, 4, 5. B 4, 5, 6, 7, 8. Let R be the relation. Let R equal to set of all order pair A comma B such that A plus B equal to 7. A plus B equal to 7. A belongs to capital A, B belongs to capital B. That is the representation of a relation in set builder form. First element belongs to A, second element belongs to B. The condition is sum of the first two elements should be given 7. What are the relation in this set? What are the ordered pair in this set? First, if we add first element, second element, it should get 7. 1 plus 4, 5, it won't come. 1 plus 5 won't come. 1 plus 6. 1 and 6 will be related because 1 plus 6 is 7. 1 plus 7 won't relate. 1 plus 8 not relate. Then 2 plus 4, 6 not relate. 2 and 5 related. 2 and 5 related. 2 and 5 related, 2, 6 won't relate. 3 and 4 related. 3 and 4 related. Then no other elements related. According to this condition, only we got 3 order pairs. 1, 6, 2, 5, 3, 4. C is equal to 7. Here, the R first element is called domain. Here the domain is. What is the domain? It is a set. What is the set? So, all the first element 1, 2, 3 is the domain set. What is the range? All the second element 6, 5 and 4. 4, 5 and 6 are the range. Now we can write in error diagram. See set A 1, 2, 3, 4, 5. Set B is 4, 5, 6, 7, 8. One is mapped with 6. One is related with 6. 2 related with 5. Then 3 related with 4. 4. In this set is called A set, but it is not the domain set. A set is not the domain set. Here, what are all the elements which are related are called domain set. Therefore, all 1, 2, 3. Therefore, the domain set, all the first element in the order pair. All the first element in the order pair is called the domain set. All the mapped elements in the B set is called, this is relation from A to B. Now, what is the codomain set? Codomain set is codomain is 1, 4, 5, 6, 7, 8. B set is the codomain set. B set is the codomain set. Now we check. Now we say, see here it is given symbolically. Domain is A such that A comma B belongs to R. All the first element of the relation. All the first element of the relation is domain set. Here B such that A comma B belongs to R. All the second element of the relation is called range set. The B set, what are mapped element and non-mapped element including is called codomain set. Is called codomain set. From this we can say domain is subset of A. Domain is subset or equal to A set. Then codomain range is subset or equal to B set. Sometimes it is equal to B set or it is a subset of B set. Range is sometimes subset of B set or equal to B set. Likewise, domain is subset of A set or equal to A set. Number of relations from one set to another set. Consider two sets, capital A and capital B. Let's consider set A has m number of elements and set B has n number of elements. Therefore, n of A is equal to m, n of B is equal to n. N of A means cardinality of the set. What is meant by cardinality? The number of elements present in the set is known as cardinality of the set. Therefore, since n of A is equal to m, n of B is equal to n, n of A cross B is equal to n of A into n of B is equal to mn. That is, A cross B has mn number of ordered pairs. A relation from A to B is basically number of possible subsets from A to B. Number of possible subsets in A to B, that is in A cross B. Therefore, number of possible subsets is equal to number of possible relations. We know that number of possible subsets of a set containing m element is 2 to the power m. 2 to the power m. Number of possible subsets in A cross B is 2 power mn. Since number of possible subsets is equal to number of possible relations, therefore number of possible relations from A to B is 2 power mn. If a set containing m elements, if a set containing n elements, total number of possible relations from set A to set B is 2 power mn. Types of relations. We are going to learn types of relations. First one, empty or void relations. Empty or void relation. The second relation is universal relation. Second relation is universal relation. The third relation, identity relation. Fourth relation, reflexive relation. Fifth relation, symmetric relation. Sixth relation, transitive relation. And seventh relation and most important relation, equivalence relation. This is a very important relation, equivalence relation. 4-marker question will be asked only from this equivalence relation. Now I am going to explain each one relation. First relation, empty or void relation. Empty means nothing is there. Empty means nothing. What is empty set? A set containing no elements is called an empty set or null set or void set. Just like that, we got empty or void relation. Empty or void relation. A relation R on set A. A relation capital R on the set A is called empty or void relation on set A if no element of A. No element of A. No element of A is related to any element of A. any element. No element of A is related to any element of A. Here, therefore, relation is equal to pi. It is a symbol for null set. This is a symbol for also null relation. Null relation is denoted by pi. Therefore, pi is also a subset of A cross A. For every set, null set is a subset. Therefore, for every relation, pi is also a subset of every relation. Therefore, pi is the subset of A cross A. Subset of A cross A. Consider an example. Let A equal to 1, 2, 4, 5. Let A set containing 4 elements. A relation R such that A comma B, A comma B, A plus B equal to 0. A plus B equal to 0. A comma B belongs to A. What are that is the condition? Sum of the two elements. If we take any two order pair, sum of the two elements must get 0. If add 1 plus 1 not equal to 0, 2 plus 2 not equal to 0, 4 plus 4 not equal to 0, 5 plus 5 not equal to 0, 1 plus 2, 2 plus 4, 4 plus 5. So, for any possible order, A plus B will not be equal to 0. Therefore, it is a empty relation. No order pair will satisfy this relation. No order pair will satisfy the relation. Therefore, this relation is known as empty relation. Another example, same element, same set, A comma B, such that A plus B greater than 9. A comma B belongs to A. A plus B greater than 9. Here the maximum is, so no, greater than 10. You take A plus B greater than 10. Here the maximum sum is 5 plus 5, 10, 4 plus 4, 8, 1 plus 2, 2 plus 2, 4, 1 plus 1, 2. Then 1 plus 2, 3, 2 plus 4, 6, 4 plus 5, 9. The maximum sum is 9, but our asking is A plus B greater than 10. So no element of A is related to any element of A. Therefore, this is called empty relations. Second one, universal relation. A relation R on set A is called universal relation on A if each element of A is related to every element of A. Each element of A is related to every element of A. It is the opposite of empty relation. In empty relation, no element of A is related to any element of A, whereas in universal relation, each element of A is related to every element of A. Such a relation is known as universal relation. Example, let set A is equal to x comma y. Set A is equal to x comma y. What are the possible relations? The possible relations are A cross A is equal to x comma x, x comma y, y comma x, and y comma y. These are all the maximum possible number of relations. Therefore, A cross A is, this relation is known as universal relation. All the elements of A is related to every element of A. X is related to X, X is related to Y, Y is related to X, Y is related to Y. So all relations, this type of relation is known as universal relation. Another example, A is equal to 1, 2, 3. Let A equal to 1, 2, 3. A relation R such that A comma B, A plus B greater than or equal to 2. A plus B greater than or equal to 2. A comma B belongs to A. The relation is A comma B such that A plus B greater than or equal to 2, A comma B belongs to A. See, 1 plus 1 is 2, minimum sum is 2, it is greater than or equal to, so possible 1 plus 2, 3, 1 plus 3, 4, 2 plus 2, 4, 2 plus 3, 5, 3 plus 2, 5, so it is always greater than or equal to. So the possible orders are, the possible orders in the relation are 1 comma 1, 2 comma 2, 2 comma 3 comma 3, 1 comma 2, 1 comma 3, 1 comma 2, 2 comma 3, 2 comma 1, 2 comma 1, 3 comma 2, and 3 comma 3, 1 comma 1, 2 comma 2, 2 comma 3, 1 comma 2, 2 comma 1, 2 comma 3, 3 comma 2, 1 comma 3, 3 comma 1 also there, 3 comma 1. So all the possible orders are mapped to this 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the possible order. The possible, all the elements are mapped to, every element of A is mapped with the every element of A itself. Such a relation is known as universal relation. Therefore, the possible order pairs are in the relation first 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 2, and 2 comma 1, 2 comma 3, and 3 comma 2, 2 comma 2, 1 comma 3, and 3 comma 1, 2, 3, 4, 5, 6, 7. There are 8 possible orders. All possible orders are belongs to this relation. Therefore, this relation is known as universal relation. A relation R on set A is called universal relation on A if each element of A is related to every element of A. We have already learned what is meant by empty relations or void relation and universal relation. Out of these two relations, the empty relation or void relation on set A is the smallest relation. Why? Because in empty relation, no element of A is related to any element of A. There is no possible of any relations. Then the universal relation on set A is the largest relation. Why? Because in universal relation, every element of A is related to every element of A. Therefore, universal relation is the largest relation and empty relation is the smallest relation. Next, we are going to learn what is a third relation, identity relation. Identity relation. A relation capital R on set A is called an identity relation if each element of A is related to itself only. Itself only. Understand the word itself only. Every element of A is related to itself only. It won't relate to other element. Example, A comma B comma C. A comma B comma C. Then identity relation is we have to find A cross A. A cross A equal to A cross A, we can write A comma B comma C cross A comma B comma C. To form an identity relation, A is related to A only, A comma A. B is related to B only, B comma B. C is related to C only, C comma C. That's all the identity relation. In identity relation, each element of A is related to itself only, because it will be bit confusing regarding reflexive relation. That is why be careful regarding related to itself only. Therefore, in set A, B, C, the identity relation is A, order pair A, B, B, C. Generally, identity relation on set A is denoted by IA. Fourth relation, reflexive relation. A relation R on a non-empty set A is called reflexive relation if every element of A is related to itself. In identity relation, in every element of A is related to itself only, whereas in reflexive relation, every element of A is related to itself, it can related to some other element also. That is the difference between an identity relation and a reflexive relation. A relation R on set A is called a reflexive relation for every order pair A, belongs to R, for every A belongs to A. A relation R on a non-empty set A is said to be not reflexive if there exists at least one A belongs to A such that order pair A not belongs to R. Not belongs to R. Identity relation is also a reflexive relation, but the converse is not true. Not true. Say an example. Consider the set A contain 1, 3, 5. R1 is the relation. We got three order pairs 1, 1, 3, 3, 5. See, 1 is mapped to itself, 3 is mapped to itself, 5 is mapped to itself. Every element of A is related to itself. 1, 1, 3, 3, 5. It is a reflexive relation. It is also an identity relation also. 1, 1, 3, 3, 5, is every element of A is related to itself only. Therefore, it is reflexive. And identity. It is both reflexive relation as well as identity relation. Consider R2 1, 1, 3, 3, 1, 5, 1. It is not, R2 is not a reflexive relation. Why R2 is not a reflexive relation? You see here in the set A pi is there, but the order for pi, is not there. So, not reflexive. It is not reflexive since pi belongs to A, pi, not belongs to R2. Not belongs to R2. Consider the relation 3. 1, 1, 3, 3, 5, 3, 1, 5, 1. Is it reflexive? Yes, it is reflexive because 1 is there, 1, 1 is there. 3 is there, 3, 3 is there. 5 is there, 5, is there. Other than this, 3 is related to 1, 5 is related to 1. It is possible even though it is a reflexive relation because each element of A is related to itself and some other element can be related. Therefore, it is reflexive. Is reflexive. Therefore, all identity relations are reflexive relations and all reflexive relations may or may not be an identity relations. We can see from this example. Seventh one and last one, equivalence relation. A relation capital R on a non-empty set A is called an equivalence relation if capital R is reflexive, symmetric and transitive. It should satisfy all the three relations: reflexive relation, symmetric relation and transitive relation. Then only the relation should be an equivalence relation. That is, For all a comma a belongs to capital R, for every small a belongs to capital A, it is reflexive. Second one, if a comma b belongs to R, implies b comma a also belongs to R, that is symmetric. Symmetric relation should be satisfied. Third one, if a comma b and b comma c belongs to R, implies a comma c also belongs to R, it is transitive. It is transitive. If all the three relations satisfied, then that relation is known as an equivalence relation. Consider an example. Consider an example. Let A be the set of all triangles in a plane. Set of all triangles in a plane. So, the relation is delta 1, triangle 1, triangle 3 and so on. The relation is congruent to the relation is congruent to. See, every triangle is congruent to itself. Every triangle is congruent to itself. Therefore, triangle 1 related to triangle 1. Triangle 1 is congruent to itself. Therefore, R is the relation is congruent. Triangle 1 is congruent to the relation is reflexive. The relation is reflexive. For symmetric, triangle 1 related to triangle 2. Triangle 1 is congruent to triangle 2, implies triangle 2 is triangle 2 related to triangle 1. If triangle 1 is congruent to triangle 2 also congruent to triangle 1. Therefore, R is symmetric. Third one, triangle 1 is congruent to triangle 2. Triangle 2 is congruent. Triangle 1 is congruent to triangle 3, implies triangle 1 congruent to triangle 3. Triangle 1 is congruent to triangle 2. Triangle 2 is congruent to triangle 3. Triangle 1 is congruent to triangle 3, implies. Therefore, this relation, it is transitive. Therefore, in the set of triangles, this is congruency is the reflexive relation, then symmetric relation and transitive relation. All the three relations are satisfied, hence it is a equivalence relation. In a plane, E is parallel to is also a symmetric equivalence relation. L1 is related to L1. L1 is related to L1 because every line is parallel to itself. Therefore, it is reflexive. The relation is parallel to L1 is parallel to L1. Every line is parallel to itself. Therefore, it is a reflexive relation. Second, L1 is related to L2, implies L2 related to L1. Is the relation is parallel to L1 is parallel to L2, implies L2 also parallel to L1. Therefore, it is symmetric. Third one, L1 is parallel to L2, L2 is parallel to L3, implies L1 is parallel to L3. Wherever the R is parallel to L1 parallel to L1 reflexive, L1 parallel to L2 implies L2 parallel to L1, symmetric. L1 parallel to L2, L2 parallel to L3 implies L1 parallel to L3 is transitive, hence the relation is a symmetric relation. These are all the examples of equivalence relation. Fifth relation, symmetric relation. A relation R on non-empty set A is called a symmetric relation if order pair A comma B belongs to R, then order pair B comma A also belongs to R. That is, if A related to B, B implies B related to A, this relation is known as symmetric relation. When a relation is not a symmetric relation, a relation R on a non-empty set A is not symmetric if there exists A comma B belongs to A such that A comma B belongs to R but order pair B comma A not belongs to R. That is not a symmetric relation. Consider an example. Consider the set A contains 4 elements 1, 2, 3, 4. R1 is the relation, we got 2 order pairs 1, 2 and 2, 3. Is it a symmetric relation? If 1, 2 is there, 2, 1 must be there. If 2, 3 is there, 3, 2 must be there. But both the order pair is not there, therefore it is not symmetric. It is not symmetric. Say 2, 1 not belongs to R1. Consider the relation R2 1, 2, 3, 2, 1, 3, 2. 1, 2 is there, 2, 1 is also there. 2, 3 is there, 3, 2 is also there. Therefore, this is symmetric relation. It is a symmetric relation. It is a symmetric relation. Consider R3. Order pair 1, 1, 2, 2, 3, 3, 4, 4 and 3, 4. Is it a symmetric relation? No, it is not a symmetric relation. Why? Because 3, 4 is there, but 4, 3 is not there. It is not symmetric. Not symmetric. Since 3, 4 belongs to R1, but 4, 3 not belongs to R3. 3, 4 is belongs to R3, but 4, 3 is not belongs to R3. Therefore, it is not a symmetric relation. In geometric examples, L1 and L2 is parallel, then L2 and L1 is parallel. E is parallel to is a symmetric relation because L1 is parallel to L2, L1 is parallel to L2, in turn L2 is parallel to L1. Therefore, E is parallel to is a symmetric relation. E is perpendicular to is also a symmetric relation. L1 perpendicular to L2, L2 perpendicular to L1. E is perpendicular to is a symmetric relation. E is parallel to is a symmetric relation. E is similar to in triangles is similar to a symmetric relation. Triangle 1 is similar to triangle 2. In turn, triangle 2 is similar to triangle 1. Therefore, these are all the examples of symmetric relation. Sixth relation, transitive relation. A relation R on non-empty set A is called a transitive relation if order pair A comma B belongs to R, then order pair B comma C belongs to R, then order pair A comma C also belongs to R. This relation is known as transitive relation. That is, if A is related to B, B is related to C, implies A is related to C. When the relation is said to be not a transitive relation on A, order pair A comma B, order pair B comma C both belongs to R, but A comma C not belongs to R, then the relation is not a transitive relation. That is, A is related to B, B is related to C, implies A is not related to C, then it is not a symmetric relation. Consider the set A having elements 2, 3, 4, 5, 6. I have given three relations: R1, 2, 2, 3, 4, 4, 4, 4, 5. Is it a transitive relation? First check 2, 2. 2 is not related to some other element. 3, 4 is there. 3, 4 is there. 4, 5 is there. But 3, 5 is not there. 3, 4 and 4, 5 belongs to R1, but 3, 5 not belongs to R1. Therefore, R1 is not a symmetric relation. Consider the relation R2, 2, 4 order pair, 3, 4, 5, 2, 5. 2 related to 4, 4 related to 5, intersection 2 also related to 5, so that order pair 2, 5 is there. Therefore, R2 is, relation R2 is transitive. Now consider the relation R3. 2, 3 one order pair, 3, 2 one order pair, 4, 5 and 5, 4. See, 2, 3 is there and 2, 3 is there, 3, 2 also there, but 2, 2 is not there. See, 2, 3 is there, 3, 2 is there, but 2, 2 is not there. Therefore, it is not transitive. R3 is not transitive. Since 2, 3, 2 belongs to R, but 2, 2 not belongs to R3. Therefore, R3 is not a transitive relation. In geometric, E is parallel to is a transitive relation. E is parallel to is a transitive relation. L1 parallel to L2. L2 parallel to L3. L1 is parallel to L2. L2 is parallel to L3. Then in turns L1 and L3 are parallel. L1 is parallel to L3. Therefore, E is parallel to is a symmetric relation. In a set of triangles, E is congruent to is a symmetric relation. Triangle 1 is congruent to triangle 2. Triangle 2 is congruent to triangle 3. In turn, triangle 1 is congruent to triangle 3. Therefore, in the set of triangles in a plane, E is congruent to is a transitive relation. E is parallel to is also a transitive relation.